This is Radhika. I am going to discuss about the power electronics subject in 5th sem electrical students. So today I am going to discuss about the uh, converters. Under that I am going to discuss about the single phase full wave control converter using R load. So here in previous classes, we discussed about the single phase half wave control converter using of RL load and also using of freewheeling diode of RL load. So actually, what is the need of freewheeling diode? Just I am discussing briefly. As in the case of single phase half wave converter with RL load, the waveform of load current is not continuous, and due to this the operating power factor of the system becomes very poor, which may gives rise to poor performance of the circuit. In order to improve the waveform of load current I0 and power factor of the circuit, a diode is connected across the load and is called freewheeling diode, and it is also called as bypass or commutating diode. So this is the need of freewheeling diode. In previous classes we discussed about the single phase half wave controlled converter using of R load. So here now we are going to discuss about the working of single phase full wave fully controlled converter using of resistive load. So in this, a full converter produces two load current pulses during one cycle of the supply voltage. In previous class, we discussed only in load current pulses will have in one cycle of the supply. So, and last class we discussed only in one load current pulse in a cycle. A half wave converter produces only one current pulse during the cycle of supply voltage. So, hence the average output voltage of full converter is more than the half wave converter. So, here this is the waveforms of full wave conversion and half wave conversion. This is the difference. So now we are going to discuss about the full wave conversion. This is the first diagram. So in this is the full wave, means in sine wave positive half cycle and negative half cycle. In full wave control converter, the pulses will be like in positive manner, because in case of here we are using the converters. Converters means it can converts AC to DC supply. So in output DC supply, the waveforms will be, it will be comes in forward bias only. So in case of half wave, this is the sine wave, and the pulse will be come only in one pulse. So that is the difference between half wave and full wave controlled converters. And in half controlled full wave converter, it converts constant DC input supply in half controlled full wave converter. It converts constant DC input supply voltage into limited range of controlled DC output voltages. The range of DC output voltage control is from 0 to maximum voltage by pi, and also it uses diodes and thyristors. It is also called as semi converter, and also it has the it converts or inverts constant AC input supply voltage into wide range of control DC output voltage. The range of controllable average DC output voltage is from minus 2 Vm by pi to Vm 2 Vm by pi. This will be clearly we will discuss in V form. Minus 2 Vm by pi to 0 is the inversion operation, and 0 to 2 Vm by pi is the conversion operation. So here this is the single phase full wave fully controlled converter circuit diagram. In this it has the circuit diagram has the 4 thyristors T1, T2, T3 and T4, and the input supply is Vm sin omega t, and the load is output voltage. Single phase full wave fully controlled converter. So actually what is the construction? It consists of 4 thyristors arranged in the form of bridge. Means we can connected the 4 thyristors T1, T2, T3 and T4. It will be connected in the form of like bridge. The load across which the output voltage to be controlled is fed to the AC supply source through this bridge. The load may be resistive or resistive inductive or any DC supply. The load may be resistive or resistive inductive or any DC motor. During positive half cycle of the supply source, in case of positive half cycle wave, T1 and T2 are forward biased, T3 and T4 are reverse biased. T1 and T2 will be triggered when firing pulses applied at a given value of firing angle alpha, and T1, T2 acts as short circuit, T3 and T4 acts as open circuit. Hence, the current flows through T1 and load and T2. Hence the current flows from T1 thyristor to load to T2. The supply voltage appears across resistive load called output voltage V0 at omega t is equal to pi, as source voltage is 0 as becoming negative T1 and T2 are reverse biased. Again I will discuss with diagram. T1 and T2 will be turned off by natural commutation. So this is the diagram of the positive half cycle. So the current will flow from positive to T1 thyristor. Here the T1 thyristor will be closed and the current will flow from here the T3 will be open. The current will flow like I0 and it comes to load. Here we are using the R load, and the current will be returns through T2. T2 is the close, and the current will be returns to negative of the supply, and here also T4 also open. So like this the thyristors T1 and T2 will be connected for positive half cycle. And also during negative half cycle the supply sources will be thyristor T3 and T4 are forward biased, T1 and T2 are reverse biased. T3 and T4 will be triggered when firing pulse is applied at omega t is equal to pi plus alpha. T1 and T2 acts as open circuit. T3 and T4 acts as short circuit. Hence, the current flows through T3 load and T4. The supply voltage appears across resistive load called output voltage at omega t is equal to 2 pi as source voltage is 0 and becoming positive. T3 and T4 are reverse biased. T3 and T4 will be turned off by natural commutation. The same operation will be repeated for subsequent cycle of the supply voltage Vs. So this is the conduction of the second wave, means in negative half cycle. The current will flow from this bottom of the supply voltage through to T3. Here T2 will be open and T1 will be open. The current flow from positive to T3, T3 to I0, I0 to load. Again the current will be reversed to T4. Here T2 will be open and it will be goes to negative terminal of the supply voltage. So like this the negative half cycle will be conducted. So it is observed that in full wave fully controlled converter using of resistive load, the load current I0 is unidirectional for both half cycles of supply. The output voltage V0 is also unidirectional, means DC. So here this is the waveforms for output waveforms and output current and gate current. So first is this is the sine wave, supply source of the supply source, that is the sine wave, and Ig is the firing pulses. The pulses will be conducted at alpha, pi plus alpha, 2 pi plus alpha, 3 pi plus alpha and 4 pi plus alpha. And the output voltage is after some delay angle alpha, the thyristor will be T1 and T2 will be conducted and it goes the maximum value of the voltage and it falls to 0 at pi, and after some delay angle pi plus alpha and the T1 and T2 will be turned off and T3 T4 will be turned on. Again it goes to maximum value of voltage and again it will be at 2 pi. The T3 and T4 will be turned off and again after alpha T1 and T2 will be conducted. Likewise the cycle will be repeats. Same as in case of I0 also same like V0, but because of the maximum values is very less because I0 is equal to V0 by R. So this is the waveforms for single phase full wave fully controlled converter using of resistive load. So here we have the equations of full wave fully controlled converter. Average output voltage from the waveform of output voltage, the average value is given by V0 is equal to 1 by 2 pi integral of alpha to 2 pi of Vs dWt. So this is the derivation only in our syllabus. We have the only derivation, no derivation, and we have the only equation of this one. So from this V0 is equal to 1 by pi 0 to pi integral of 0 to pi and Vs dWt. After calculation of this one, 1 by pi integral of 0 to pi Vm sin omega t d omega t. So finally we will get Vm by pi of minus cos omega t of g of pi. So full wave fully controlled converter, the finally output voltage V0 is equal to Vm by pi of 1 plus cos alpha. In case of alpha is equal to 0 degrees, the output voltage is 2 Vm by pi. In case of alpha is equal to pi by 2, the output voltage is Vm by pi. In case of alpha is equal to pi, the output voltage is equal to 0. It is observed that as the firing angle alpha increases, the output voltage V0 decreases. The average load current I0 is equal to V0 by R, that is Vm by pi R into 1 plus cos alpha. So circuit turn off time Tc is equal to the pair of thyristor T1, T2 and T3, T4 are reverse biased for pi radians alternatively. Hence the circuit turn off time is given by Tc is equal to pi by omega. This is the circuit turn off time. So remaining time the circuit will be in on position. So this is about the single phase full wave fully controlled converter using of resistive load. So in this diagram, this is the main circuit diagram of single phase full wave fully controlled. So here in this, the source voltage Vs is Vm sin omega t is improved to the circuit during the positive half cycle. The thyristor T1 and T2 are forward biased at omega t is equal to alpha. The thyristor T1 and T2 are triggered. Hence, they start conducting causes a load current I0 will flow to the load. At omega t is equal to pi, the load current becomes 0 and the source voltage is reversed. Therefore, the thyristor T1 and T2 are turned off by natural commutation. During the negative half cycle, the thyristor T3 and T4 conduct from omega t is equal to pi plus alpha to omega t is equal to 2 pi. At omega t is equal to 2 pi, the load current becomes 0 and the source voltage is reversed. Therefore, the thyristors T3 and T4 are turned off by natural commutation. The above sequence of events are repeated for each cycle. So, in the waveforms, the source voltage or input voltage, firing pulses T1 and T1, T2 and T3, T4, load currents and output voltage. So now this is the class for single phase full wave fully controlled converter using of R load. Now we will watch the YouTube video lesson for single phase full wave fully controlled converter using R load.
In case of fully controlled bridge rectifier, we are using 4 SCRs. The circuit consists of 4 thyristors T1, T2, T3 and T4 and a voltage source Vs and a resistive load. Here thyristors T1 and T2 are simultaneously triggered and pi radians later, thyristor pair T3 and T4 are triggered. When A is positive with respect to B, the supply voltage waveform is shown as VAB. When B is positive with respect to A, supply voltage waveform is VBA. VAB is equal to minus VBA. So this one is VAB when A is positive with respect to B. So we can draw VBA. VBA is minus of VAB. So this one is VAB and this one is VBA. During the positive half cycle, here plus and here minus. That is A is positive with respect to B. So here it is positive. So T1 is forward biased, T4 is reverse biased. This one is negative. Therefore T2 is forward biased and T3 is reverse biased. So we can say that during the positive half cycle, T1 and T2 are forward biased, but it does not conduct until a gate signal is applied between gate and cathode terminals. Consider firing angle alpha is equal to 30 degree. So at alpha is equal to 30 degree, we are giving gate pulses to T1 and T2. So when the gate pulse is given to the thyristors T1 and T2 at omega t is equal to alpha, it gets turned on and begins to conduct. When T1 and T2 is on, this input voltage is applied to the load through the path Vs, T1, load, T2 and back to Vs. So this one is the direction of current and this plus appears here and this minus appear here. Therefore, the output voltage V0 is equal to Vs from alpha to pi. So this portion appearing across V0. During the negative half cycle, here minus and here plus. So A is negative, T4 is forward biased and T1 is reverse biased. And B is positive, so T2 is reverse biased and T3 is forward biased. So we can say that during the negative half cycle, T3 and T4 are forward biased and the thyristors T1 and T2 are reverse biased. When the gate pulse is given to the thyristors T3 and T4 at omega t is equal to pi plus alpha, thyristors gets turned on and begins to conduct. So when T3 and T4 are on, the input voltage Vs applied to the load through the path Vs, T3, load, T4 back to source. Here also the current flow direction is this one only and the voltage VBA, here it is P and this one is A. So the voltage VBA appearing across the load. From the waveform it is clear that VBA is this one. So this waveform appears across the load. Again, during the positive half cycle, T1, T2 becomes forward biased and T3, T4 becomes reverse biased. And we are applying a gate pulse at 2 pi plus alpha. Thyristors T1 and T2 conducts. We can conclude that during the positive half cycle, T1, T2 conducts and the voltage VAB appearing across the load. T1, T2 conducts and the voltage VAB appearing across the load. During the negative half cycle, T3, T4 conducts and the voltage VBA. This one is VBA appearing across the load. T3, T4 conducts. Again T1, T2, then T3, T4. So here the load receives the voltage during both positive and negative half cycles. And the average value of output voltage can be varied by varying the firing angle alpha. In case of resistive load, both output voltage and output current are in phase. So I0 is this one. Same as that of V0 with reduced magnitude, because I0 is equal to V0 by R. Next is voltage across T1 and T2. During the positive half cycle up to 0 to alpha, T1 and T2 are in the off state, that is act as open switch. So this voltage appears across VT1 and VT2. This voltage from 0 to alpha. From alpha to pi, T1 and T2 are short circuit on. So 0 voltage appearing across VT1 and VT2. Again, during the negative half cycle, T1 and T2 are in the off state. Therefore, the negative voltage, this voltage appearing across the SCR. Again, from 2 pi to 2 pi plus alpha, T1 and T2 are in the off state. So this voltage appearing across the thyristor. Again, during the negative half cycle, T1 and T2 are off. Next is voltage across T3 and T4. During the positive half cycle, T3 and T4 are off. So this voltage VBA appearing across the thyristor T3 and T4. This voltage. During the negative half cycle, from pi to pi plus alpha, T3 and T4 are off. So this voltage appearing across T3 and T4. This voltage. And again, during the positive half cycle, T3 and T4 are off. So this VBA appearing across the T3 and T4. Next, we have to find out the RMS and average value of output voltage. We know that V0 average is equal to area divided by base. So here area is integral alpha to pi, this one, Vm sin omega t into d omega t divided by base. Here base is set as pi because the waveform repeats at an interval of pi divided by pi, which is equal to 1 Vm divided by pi integral alpha to pi sin omega t into d omega t, which is equal to Vm by pi integral sin omega t minus cos omega t minus cos omega t with limits alpha to pi, which is equal to minus Vm by pi. We can apply the limits cos pi minus cos alpha, which is equal to minus Vm by pi. Cos pi is minus 1 minus cos alpha, which is equal to Vm by pi into 1 plus cos alpha. So V0 average is equal to Vm by pi into 1 plus cos alpha, and I0 average is equal to V0 average divided by R. Next is V0 RMS, which is equal to integral alpha to pi area square Vm square sin square omega t into d omega t divided by pi root, which is equal to Vm divided by root pi, root of, instead of sin square omega t, we can write 1 minus cos 2 omega t by 2. So integral alpha to pi 1 minus cos 2 omega t by 2 into d omega t, which is equal to Vm by root 2 pi. This one, root of integral alpha to pi 1 minus cos 2 omega t into d omega t, which is equal to Vm by root 2 pi root of integral 1 into d omega t is omega t with limits alpha to pi minus integral cos 2 omega t is sin 2 omega t divided by 2 with limits alpha to pi equal to Vm divided by root 2 pi root of pi minus alpha minus 1 by 2 sin 2 pi minus sin 2 alpha. Sin 2 pi is 0, which is equal to Vm by root 2 pi root of pi minus alpha plus sin 2 alpha divided by 2. So V0 RMS is equal to Vm divided by root 2 pi root of pi minus alpha plus sin 2 alpha by 2, and also I0 RMS is equal to V0 RMS divided by R. Thank you.
Hi all, today we are going to discuss about single phase half.
So now we watched the YouTube video for the single phase full wave fully controlled converter using of resistive load. So this is the about single phase. Just we will discuss briefly. Fully controlled converter means that both the half cycles are phase controlled. In this type of converters, the power flows in either directions. Hence, these are also called as the bidirectional converter. In this, the single phase full wave converter using resistive load. So it consists of 4 thyristors which are connected to in 2 parallel branches. Let us consider the source voltage Vs as the Vm sin omega t is impressed to the circuit. So here So in this is the summary of the load current I0 is unidirectional for both half cycle of the supply voltage. The output voltage is also unidirectional, that is DC. The average DC output voltage V0 is equal to Vm by pi into 1 plus cos alpha. As the firing angle alpha increases, the average DC output voltage will decreases. The controllable range of average DC output voltage is from 0 to 2 Vm by pi. So now we have the few quiz questions and few frequently asked questions. So this is the class for single phase fully controlled converter using of R load. In next class I am going to discuss about the inverters. Thank you.